Hello and welcome to lecture 11. So, just a reminder, you have an exam coming up next week and a quiz coming up next week and a quiz that opens up today, and it will close on Wednesday at 11:59 p.m. So, 2 more quizzes and a final exam. Check your syllabus for the dates on those. This week, I'm only going to give 4 lectures for this week, and they'll be relatively short. I just want to give you enough time to catch up if you need to, and to study for your final. So check on the syllabus. Let's do a brief review from last lecture. So if you remember, we discussed lightning and thunder. We talked about how thunder is just the sound that lightning makes. So all lightning has thunder, and there cannot be thunder without lightning. We talked about Earth's Fairweather field and static electricity. So generally, if there's not any storms outside, there's not enough ambient static electricity to create lightning. Storms work up to build static electricity so this lightning can happen. Now, what happens inside of these storms? You have a cold cloud. The top of it is predominantly ice particles, and the bottom is rain, and that allows the charges to separate, where the positive charges go to the top of the cloud, and the negative charges go towards the bottom of the ground. The approximate speed of thunder is 0.2 miles per second, so 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi. That means that the thunder created by the lightning is by lightning that is 1 mile away. So every 5 seconds, that adds 1 mile away to the lightning. And we talked about lightning safety. You don't want to get struck by lightning. Alright, let's get into the lecture for today. So today we're going to talk about MCSs and downbursts, and then we'll talk about supercells. So a mesoscale convective system, also called an MCS, is an organized group of severe thunderstorms. So there are individual severe storms within an MCS, but they're so close together that the precipitation merges into one big line. So while individual storms within the MCS may grow and decay, the whole entire MCS can persist for about 10 hours, and they can extend about 100 miles in at least one direction, and they produce hundreds of severe weather reports. So you can have, usually they're called linear system, but they can also be circular or oval or curved. And they're most common in the plains, but you really get them everywhere. They kind of form in the plains and then they move east. They tend to form in the late afternoon and reach peak strength in the late evening and overnight. So MCSs account for up to 70% of spring and summer precip in the plains. They produce large swaths of hundreds of severe weather reports. It's primarily severe hail and severe winds, as well as flash flooding because of the rainfall. However, you can have tornadoes embedded within the line. So, like the other storms we talked about, it has the same ingredients for severe storm formation, which you can use the acronym SLIM. So shear, lift, instability, and moisture. So you need a warm, moist, unstable air mass. So this is needed for all types of storms. You need moderate to strong vertical wind shear. This is only needed for severe storms, but MCSs commonly produce severe weather, so you oftentimes have pretty good strong vertical wind shear. You need strong rising motion over a large area, and that's what you need to make a lot of storms, which you get in these linear systems. So one way that these are formed is through the low-level jet, or the LLJ. So what happens with the low-level jet is it forms these southerly winds that bring in this moist tropical air mass from the Gulf. So it advects warm, moist air from the Gulf of Mexico into the plains. So this kind of acts as fuel for these storms. The second ingredient is moderate to strong vertical wind shear. So the wind speed increases significantly at the top of the boundary layer, and this can create a low pressure system at the surface. You also need strong rising motion over a large area. So if you have like a low density air mass, you can have this widespread, large scale rising motion. And so that's why the low level jet is effective for creating MCSs, and this is why a lot of them happen at night or in the overnight hours. So, a lot of the the MCSs are formed through troughs and cold fronts. So basically what happens with troughs is you get a strong rising motion over a large area because there's upper level divergence, and the air at the surface goes to fill in the diverging air up top because it's like a vacuum. So it results in rising motion. So, and you also have an unstable troposphere that enhances rising motion because it's bringing in this cold air. Another thing that these troughs bring in is cold fronts, so it also helps with strong rising motion over a large area. What happens is you have the frontal boundary and it pushes up underneath the warm air, and usually this rising motion will be along like a band, so you'll get this linear characteristic. And this line is called a squall line. So MCS and squall line pretty much mean the same thing. The reason why it forms an MCS instead of like a supercell has to do with the bulk wind shear. So if you have if most of your wind is predominantly southerly and it's going towards the north, and you see that in your you can see it on weather maps and stuff. If you look at 0.6 kilometer bulk shear, if you see the wind barbs pointed towards the north, you're going to have a problem where your storms are going to start to merge into each other. Whereas if the winds are westerly and pointing towards the east, you're not going to get this contamination. So the first situation where it's southerly winds in the bulk wind shear, you're going to have more of a linear storm mode. Whereas if you have this east or this westerly wind, it's going to prevent the storms from forming this line. So you'll get supercells over, instead of getting like the MCS linear formation. See, you can see like they're all kind of blended up together. You can get these bowing formations because the wind speed in some places are faster. So you'll often see these in developed MCSs where you'll get these bow echo structures. So you can look for that for possibly severe weather events. But they can also look like a straight line, like you see kind of right here. It looks pretty linear. So yeah, they're typically just form along a cold front. So yeah, you can imagine that right along this boundary here, you have cold air pushing through. So it's just really a good indicator of where the boundary is. So we'll talk about the cold pool. So this right here, these clouds, this is the same thing as looking at this on the radar. So this rain falls through the downdrafts of individual storms. And it drags air downwards and it cools the air as it evaporates. So each storm has its own individual cold pool. So they drew a big cold pool, but each storm has its own individual one. However, they get, when they get close enough, so like right here, for instance, like you don't really see it, like down here, the storms are more individual. but up here they're kind of more squished together. So in that situation, the cold pools can start to merge into one very large cold pool. And then you just have like a longer outflow boundary. So the outflow boundary is where this cold air starts to move outwards from under the storm, and it will be larger in length than if it was just an individual supercell. So, one large cold pool with one large outflow boundary is a key step for the MCS formation. So, when you have a large cold pool, you have like this large region of very dense air, and as it advances forward, it kind of pushes up air out in front of it, so it propagates itself. So what happens is more storms are able to form out ahead of it, and the MCS is sustained. So this is what causes storms to act together as a system and produce severe weather over a large area. So the cold pool is what sustains the MCS. Sometimes this outflow boundary can get too far ahead of the storm, and when that happens, you can pretty much pack up your bags and go home, because once the outflow boundary gets too far ahead of the MCS, it's contaminated, and it is not going to support the development of the MCS any further. Okay, so this is what I was kind of mentioning. So squall lines occasionally develop into an appearance of a bow echo on the radar. So what happens is strong winds behind the lines of storms can effectively push the precip forward. And this usually happens in the middle, like in the top to bottom, like north to south. It kind of happens in the middle of the MCS. So these are curved areas of higher radar reflectivity within the squall lines. Yeah, so you can see that the storm is a little bit more powerful where the bowing is occurring, and that's because there's straight line severe surface winds, and it's from the outflow of the MCS. So the strongest straight line winds occur at the part of the bow echo that's farthest forward in a back to front sense. Yeah, so it's basically just propagating forward faster at these places because the boundary, this cold pool is like stronger, and so it pushes forward more and it has more lift. Derechos. It's a widespread long-lived windstorm. And they're kind of associated with squall lines and bow echoes, but they're not quite the same thing. They have very specific criteria, and you can't just look at a storm on the radar and say, oh, yeah, this is a derecho. Like, if you hear a scientist say that, or somebody on TV, maybe, but you can't really assess if something is a derecho until after the fact because of the specific requirements that must be met for it to be considered a derecho. So here is the SPC definition. There's several different definitions online, but they're pretty much almost all the same. I trust the Storm Prediction Center. So this is how they classify it. If the swath of wind damage extends for more than 250 miles, includes wind gusts of at least 58 miles per hour, along with most of its length, and also includes several well-separated 75 mile per hour or greater gusts, then the event may be classified as a derecho. So the reason why it is difficult to classify something as a derecho until after the effect, or after the fact, is because you have to go out and do damage surveys for the derecho and see if you do meet this criteria of 250 miles. You have to look for straight line wind damage, and as well as like indications of these hurricane force winds. So yeah, it's difficult to get a derecho. They're not particularly common, but they do happen. Maybe like a couple times a year. And yeah, so yeah, very specific criteria for these. So they can produce destruction similar of tornadoes. So you can kind of like see, like in a tornado, you'll see like these lines of damage, like out. You'll see like trees going down in a straight line, and then the derechos, they kind of have straight line winds, and so you'll see a lot of trees down over a large swath of area instead of these little bands. So here's a radar loop of a derecho. I'll click it. Okay. Yeah. See, it's huge. They're really big. Like, and you can see that kind of cold pool effect out in front of it, and it's kind of... Oh, there was 2 of them this day, yeah. There's the second one. Okay. Yeah. So... They're really large. So here is the climatology of the derechos. So this is between 1980 and 2001. The approximate number of times you've had moderate to high intensity derechos at certain points. So if they've been affected by 3 or more derecho events, they're shaded yellow, orange, and red. So the most common places to find a derecho is in the Midwest and the Great Plains. I would say especially the Midwest, but yeah, you do also get them in the Great Plains in this area. But over in this Illinois, Indiana, Ohio area, they form pretty frequently compared to other areas in the United States. So this northwestern portion, like the Midwest, it's primarily in the warm season. So yeah, you'll see like a derecho form in the summer here. And then the southeastern portion is primarily in the cool season. So you really need that like troughing pattern to get these to form, and the troughs do not sink down as low in the summer. They kind of sink to right here. So you kind of get the more northerly derecho formation in the summer as compared to cooler seasons like spring and fall in this area. So here is like a derecho from June 29th, 2012. So this is what it looked like on the radar. You can kind of see that bowing feature, but they kind of look round. And this is the damage path, so I'm assuming that these are like wind reports and stuff. You can kind of see a couple of these red ones. I think those are probably tornado reports. So on the edges of it, you might be able to get an embedded tornadoes, but it's mostly straight line winds. And here is the storm reports for the SPC. So you can see these blue ones right here that are plentiful. These are kind of like straight line wind reports, and you get a couple of hail reports and 2 tornado reports. But you can see there are like a lot of straight line wind reports in this area for this storm. So very powerful. So this is kind of what I was talking about before. So what type of wind shear? You need the wind shear to be parallel to the lifting mechanism, so like a cold front. So this means that the shear vectors, the precipitation is advected along the line, not off the line, which supports individual cells merging into a long line. So this is like that northerly wind I was talking about. You want these storms to have like an overall, like on the whole, bulk shear means like from the surface to aloft, what is the average wind direction and speed? So the bulk shear is kind of pointing more north in this situation. And so that means that these storms are going to combine and bleed over into each other. Now, if these were pointed from the west to the east, these storms would not bleed together. So you would get something that looks more like this one up here, or this one down here. Just these individual single cell or multi-cell storms, not this line formation. And a lot of times you'll get like a formation where you'll have it and it will be moving east and you'll get supercells, and then eventually it changes storm mode into MCS as the wind speed changes direction, or the wind changes direction. So like if it moves out this way and then the low level jet forms, it can shift the overall wind direction from westerly to southerly and form into an MCS from supercells. Okay, next PowerPoint. So we just talked about MCSs, and we talked about the ingredients for formation, SLIM. We talked about how cold pools help to sustain the MCSs, and we talked about bow echoes and derechos. So now we're going to talk about downbursts. So here's a really nice picture of a downburst. A downburst is a column of rapidly descending air that can form in the downdraft of any precipitating cloud. So it can be a severe thunderstorm or it can be a weak rain shower. But what happens is this cold air hits the surface and it is forced to diverge out. So you can see it here. It's kind of going out in all directions. And it creates like a curl of dust, precipitation, and cloud at the edge of the downburst. So this curl is just this vortex ring. So you can see it hits the ground and then it kind of goes back up and it curls back inwards. So it's at your at the edge of your outflow. So it's accompanied by severe straight line surface winds, intense wind shear, and extreme turbulence. Yeah, this is like, you don't want to be, this is why they put radars at the airport, is because of these downbursts. Like, you don't want to fly your plane through one. So here's some really good pictures of them. So a downburst is a column of rapidly descending air that can form in the downdraft of any precipitating cloud, from a severe thunderstorm to a weak rain shower. Upon hitting the surface, this air is forced to diverge out. So that's what we just talked about on the last slide. So here are the pictures, and you can see it here, how it is spreading out as it hits the surface. It's also spreading out here as it hits the surface, and it's picking up this dust. So there's different types of downbursts. They're classified by size, and they're also classified by if the environment is moist or dry. So microbursts are downbursts that are less than 4 kilometers across, and macrobursts are downbursts that are greater than 4 kilometers across. They're also very difficult to forecast because they only last a few minutes, but during those few minutes they can cause extreme damage. So they form when the rain falls from the lower part of a storm or shower into the dry air below the cloud base. So there's dry air around this cloud base. Then the water that's falling out of it partially or fully evaporates or sublimates, if it's ice or hail falling out, into the dry air. Then you have evaporation and sublimation. This requires latent heat. Remember, evaporation is a cooling process, so it's taking up heat from the outside environment. So it will cool the air. Thus, the air becomes more dense and it starts to sink downwards rapidly. So, and also you can have this precipitation that's like loading up in here. Like, you can have a lot of, like, a strong updraft that's holding this all up, and once you get this downburst, it all just falls out at once. So, in the case where liquid all evaporates into the dry air, you get something called virga. So, virga is rain that evaporates before it hits the ground. So you can kind of see there's a pocket of dry air aloft, so there's dry air up here, and there's significant evaporation happening, and a downburst is possible in this situation. It's just forming. So as you can see, it's raining out and it's evaporating into this dry air, so the rain doesn't make it all the way to the surface. So this is a visual cue that a downburst may happen. When the dense downdraft air hits the ground, it's forced to spread out rapidly in all directions. So you get severe straight line winds in a radial pattern, and the wind speeds can reach over 100 miles per hour. So the winds along this outflow boundary are so strong that they can start to curl upwards, as you can see in this diagram and we saw before. So this creates intense wind shear, and it can create extreme turbulence. So whenever you get like any sort of wave, like rotor wave off of a storm, that's not really a good environment to fly a plane in, because it creates turbulence. It's the same thing with flying like over a mountain. Like, you don't get too low to the ground when you're flying in the mountains, because the mountains also create these curling winds, and it's primarily responsible for turbulence. That's the same thing with these downbursts. You can get really strong turbulence from this curling motion. So typically you avoid flying into that with your aircraft. So there's dry microbursts, dry microbursts and wet microbursts. I guess you can also have them on a larger scale as well, so we'll just call them downbursts. So with the dry downburst, all the precipitation evaporates and sublimates before hitting the ground. And it's hard to see because there's not really anything to see. So it's like that Virga situation. But then you can also get a wet microburst, where not all of the precipitation evaporates or sublimates, so you can kind of see this big blob of rain hitting the ground, and they're both equally dangerous. So, and you can go from a dry to a wet downburst. So like initially here it's a dry, it's not yet at the ground, but there is still this cold air that's moving off of this storm. Honestly, it does look like some of it's hitting the ground in the background, but you can kind of see this blob, like this main downburst area has not yet hit the ground. But then as the storm progresses and the precipitation all falls, it just unloads, and you can kind of see that curling motion as it hits the ground. Very powerful. So we're going to talk about the difference between the downburst and tornado damage. So they both can cause like a very similar magnitude of damage, but tornado damage kind of occurs more in this like spiral shape. I honestly, to me, when I look at a tornado damage, it kind of looks like it's in a line. Like if you look at the damage path, it just looks like a straight line, and you can kind of have some curvature in it if it like wraps around the tornado, but if you look at it over a large length, it just looks like somebody bulldozed down everything on the ground. Whereas in a downburst, you have this radial damage pattern that occurs in all directions, so everything is kind of in the same direction. For a tornado, it's more linear damage, whereas in a downburst, you have this radial damage from the point of impact, because the winds spread out in all directions when the downburst makes contact with the ground. They look similar on radar velocity displays. So remember, it was red and green, but we switched the color to blue. So when we have red on the green in the display, it means that there is either divergence or there is rotation. And the only way you can really tell the difference is to know where the radar is. So, they have an example, and I'll explain it. So, here's the radar site. And this blue means it's going towards the radar, and the red means it's going away from the radar. So this is a downburst. because the winds are spreading out as they make contact with the ground, so there is diverging air. However, if we put it over here, we have the blue that is moving towards the radar and the red that is moving away. As you can see, it's kind of making this motion. So it's a tornado, or at least some rotation that looks similar to a tornado, because it is oriented in a way that shows us that the air is rotating counterclockwise. So, downburst in aircraft. One of the most dangerous weather phenomena to aircraft and pilots is the downburst. So, let's explore exactly what happens when a pilot flies into a downburst. So, a headwind is a wind blowing in the opposite direction of the plane's motion, which increases the lift, and then, so it gets up under the aircraft and it adds more lift. If you have a tailwind, it blows behind the aircraft into the same direction, and so it decreases the lift. So, this is based off of a true story. I don't know if they'll get to this in this course, but yeah, this happened, and this is why we have radars at airports. It's because of this specific phenomena. So, what happens is the plane approaches the downburst, and it experiences this headwind. So it gets extra lift, because you can see it's blowing this way into the plane and underneath the plane, so it's going to lift up. Then it gets into the core of the downburst. The horizontal wind speed is 0, but it decreases the lift because you were having extra lift, and now you don't have that extra lift, so the lift is going to go down. And then you also have this sinking air, this really rapid motion of downwards moving air, and it will push the plane downward. Then, as the plane leaves the downburst, it will get a tailwind, which will again decrease the lift because it's pushing up on the tail of the plane, which will point the nose of the plane more downward. And this is the part where you kind of have the high potential of crashing into the ground, since step 2 already pushed you closer to the ground. Step 3 can really seal the deal. So, yeah, not good. This happened in Arizona or something like that, and it happened to 2 planes on the same day, I think. I don't know. It was in the 70s. And since this happened, there's not been another weather-related plane crash since. There is not, because we added a bunch of radars at airports. So when you feel turbulence on the plane, you can feel safe in knowing that this kind of weather-related plane crash has not happened since this event. So they are much more well-informed of where to fly and what the weather is doing outside to prevent these type of things from happening. So here are all the special radars that were deployed nationally at large airports. So these were put up to prevent these crashes. So you can see we have 2 of them in Oklahoma, but you get pretty good coverage. The only reason why we don't have them out here as much is because it's kind of mountainous, but you can still get the spatial coverage that you need. This is where the microbursts are predominantly happening, so, you can see where you need to see. So, the terminal Doppler weather radar is smaller radars than the WSR-88Ds, and they have smaller spatial coverage, but they put them at the larger airports. However, at the smaller airports, you can also use regular radar data. So this just gives us special extra coverage, but we also put up a lot of other radars on top of that. So we have really good coverage of the United States in regards to radar, and we can kind of figure out where to take the planes. Okay. Let's see. Okay, so we just finished talking about the downbursts, and we talked about if they can be wet or dry, and we talked about the difference on radar between downbursts and tornadoes, and then we talked about the danger downbursts pose to aircraft. So now we will talk about supercells, which is just the best thing that ever happened in meteorology, in my opinion. I love supercells, and this is what I've been waiting to teach. So there it is in all of its glory, the supercell. So the definition of a supercell is a severe thunderstorm with a rotating updraft. So you'll see this spiral appearance in them due to the rotation in the mid-levels. But all that's really required for it is for the updraft, so the area where the air is moving upwards, it needs to be rotating. So this updraft rotation can translate into a rotation at the surface. So the supercells are what's best at producing the tornadoes. They're the storm that's best at it, but they also produce severe wind and hail. So, and the reason why is because they're not attached to any other storms, like we saw in the MCS. These are independent, and so they're much easier to get rotating than it is to get like a whole line to start rotating. So we talked a little bit earlier about vorticity. I touched on it, but we'll talk about it. So vorticity, the simple definition is the rotation of a fluid at a point. So at a single point, like what is the angular velocity of this fluid? This can be caused by a change in wind direction or a change in speed. So this is the wind shear we were talking about. So a change in speed or direction. So you can see here as you go aloft, you have like, if you have a faster wind at the ground and a slower wind aloft, it can create this region of rotation. Likewise, the other way around, if it's faster aloft and slower at the surface, you can get this type of rotation. But this is also the case in like a trough. So this, you can have vertical and horizontal wind shear. So it could be slower in the south and faster in the north, or vice versa. Rotating objects and fluids spin around on an axis. So this is called the axis of rotation. Horizontal vorticity is the rotation around a horizontally rotated axis. So, for instance, like a bicycle wheel that is, yeah. So if it's rotating like this, it's yes. Okay, so this is horizontal vorticity. It's a little confusing, but this is how the spin is moving. It's like a horizontal spin, and it can create like this vertical motion. And then vertical vorticity is when this axis is like, see, for instance, this axis of this bike wheel is like pointed towards you, and like it's like a flat line. It's on the well, I guess technically it's on the y-axis, and then this one is on the z-axis here. So vertical vorticity, the axis of rotation is on like the z-axis, and so like a record on a record player, this is a example of vertical vorticity because the axis of rotation goes up and down. So here's the structure of the supercell. They have the mesocyclone it has a large amount of vertical vorticity. So the mesocyclone is like the rotation within the cloud, and we have to figure out how this vertical vorticity is produced to create this. Mesocyclones are like kind of like the precursor for tornado. Like, you can have storms that form a mesocyclone and then don't have a tornado, but if the mesocyclone can get tilted in the correct way, it will produce a tornado. So what happens is you have this horizontal vorticity, but it can turn into vertical vorticity and vice versa. So it changes the direction of the vorticity, but it doesn't change the magnitude. So it's not spinning any faster. It just tilted. You need this vertical vorticity for supercell formation, and you can get this by the tilting of the horizontal vorticity. So tilting is really important for supercell formation. So you can also have vorticity advected, just like other things. So vorticity advection is actually really important. It's not as important as where the vorticity is as where the vorticity is going. Like, that's where you predict where the severe weather is going to go. You don't look where there's positive vorticity, you look where there's positive vorticity advection. So, an example of positive vorticity advection is inflow winds that advect vertical vorticity along the ground and towards and upwards into the storm updraft. So you can see this vorticity here is being advected into the storm, and it's also tilting from horizontal vorticity to vertical vorticity. Okay, it can be stretched as well. So this can happen in a fast updraft. So think of it like it's like an ice skater. So when you have stretching of a column of air, it tightens up, so it's able to rotate faster. So yeah, like, you know how you have figure skating, or like you're spinning in a chair and you put your arms out and then like you pull your arms in, you'll start to spin faster. That's the same thing with storms. So if you can get the vorticity to be stretched by a fast updraft, you can get this spin that strengthens the vorticity. And so the stretching is super important to create tornadoes. So we got a couple of steps. So what happens is, first you have this vertical wind shear that creates this horizontal vorticity. So this is speed shear generating horizontal vorticity. So yeah, you can see you have like these slower winds and the faster winds up here, and it creates these tubes along the ground. So these are horizontal vorticity. You kind of have like these tube areas. Then there's an updraft, so there's upwards motion, and this upwards motion starts to affect this vorticity into the vertical. So it goes from horizontal vorticity to vertical vorticity. This also will stretch out the vorticity, which will make the rotation faster. So this updraft is kind of tilted, and that's a characteristic of severe thunderstorms. Then, when your updraft gets strong enough, it will tilt the rotating air nearly vertical, and it stretches it even more. So it goes from like this to like this with a stronger updraft. And then the column of rotating air becomes really strong, and it's stronger because of this updraft, like the strong updraft. It's like stretching it out and making it rotate faster. So here are the first three steps shown. So this was the horizontal vorticity, and this was created by wind shear. Then it's tilted by the updraft into the vertical, and then the updraft tilts it even further into the vertical and stretches it out even more. So it starts to stretch, and then it stretches even more, and now it's rotating really fast, and you can see there's a tornado on the ground in this situation. So this first one right here, this step one, this is what a mesocyclone is. Like, this is all mesocyclone, but it becomes a tornado once a funnel cloud hits the ground. So mesocyclones, as the updraft stretches and strengthens, the updraft begins to rotate. So a mesocyclone is a cyclonically rotating updraft. So yeah, in my opinion, this is where the mesocyclone starts, but because it is rotating cyclonically, technically it's just an angle. But yeah, I guess you could technically say this is also where the mesocyclone starts. Just learn different things at different places, I guess. But yeah, the bottom line is the mesocyclone is the rotation within the cloud, and it becomes a tornado. It's like a mesocyclone is not necessarily a tornado. So the mesocyclone can be anywhere from 2 to 10 miles wide, and the rotation is up to 100 times faster than the rotation of Earth on its axis. So here's our tube. This is a tube of vorticity. It becomes the most vertical far up above the ground, and still like in the middle of the storm. So here, this is where it kind of becomes most vertical up here. As you can see, it's not perfectly vertical down here, but it's more vertical up here. This is kind of a better example, I think. Yeah, so it's not perfectly vertical down here, but it's closer to vertical in the middle of the cloud. So, the vertical vorticity in the mesocyclone is strongest in the mid-levels of the storm, between 3 and 7 kilometers off the ground. Then, around this, oh yeah, we don't need to talk about it. But a low pressure forms in the middle of the mesocyclone. If you want to talk about this in detail, take severe and this is severe and unusual weather. Take severe storms. I think it's called severe storm forecasting or something like that. You take it with Dr. Tom Galarno. I took that class with him, and he will get all into the dynamics of this. But it's pretty advanced, and it's a lot of steps, so we will just say that a low forms here, and we won't get into it because it's very dynamical. But, and honestly, I think if I was a better meteorologist, I probably could explain it a little bit better, but I don't want to explain it wrong and then mess it up, because you can get a good explanation from a professor here that will be able to tell you more succinctly than I could. But anyway, long story short, this low pressure center, it enhances the rising motion into the updraft. So you get stronger inflow because the low pressure creates this vacuum up here, and so it's going to increase the speed of the updraft. So when you increase the speed of the updraft, you take that horizontal vorticity coming in, and it becomes more vertical. And then there's also stronger stretching, and the stretching effect is what creates this lower pressure. So it kind of creates this positive feedback cycle, and that's why supercells can persist for a long period of time. They are self-sustaining. So rising motion in the supercell updraft is fast, 45 to 90 miles per hour. So yeah, they are really ingesting air. And the mesocyclone rotation is what gives the supercells their characteristic spiral appearance. So you can see this rotation around here. That is the mesocyclone rotating. So mesocyclone is a larger area of rotation, and then the tornado forms out of that. Here's a video that she says to play at 2 times speed. Whoa. Okay. Oh, that's not what I meant to press. I'm gonna play it fast. Whoa. Okay, yeah. So here you can see the updraft is right here. So you have the mesocyclone, and it's this big overall rotation in here, and this air is it's like horizontal vorticity down here, and then it is pulled in by this updraft right here. So this is the updraft, and this horizontal tube of rotation gets flipped into the vertical. Okay, this is another one. It didn't really have that much spin on it. This one was good though, like, yeah, so horizontal flip to vertical, and you can see it kind of like going up and being flipped into the vertical, and it's stronger up here, like in the mid-level of the storm. That's where the mesocyclone is the strongest, and it's where it's stretched the most, and that is because of the enhanced stretching effect, because the updraft is strongest up there. And the downdraft is over here. It's like this rain. And if you get the rotation strong enough, you can kind of get the updraft to the downdraft to rotate around. So that's how it becomes rain wrapped. If it pulls this rain around to the other side, then you can get a rain wrapped tornado, and that's very dangerous. Okay. I don't know what that video is, but if you want to watch it, be my guest. So yeah, this is what I was talking about. So this is the updraft area. So you kind of get this like notch. That's what it looks like in a radar image. So we're looking down right now. So this is the updraft region. So it's pulling in this air, and so over here you can say it's like horizontal vorticity, and as it's pulled into the updraft, it flips and it becomes vertical vorticity. It's tilted into the vertical. Then you have like a forward flanking downdraft. So your air is like your rain is separated from your updraft because of the storm tilting on the whole. So your forward flanking downdraft is like this heavy rain area / hail. So your updraft's here, your forward flanking downdraft is here, so this is your original one. But this updraft can get rotating so much as it pulls in more vorticity and stretches it, that it wraps this forward flanking downdraft around the storm, and that's how you get this rear flanking downdraft. So it can, it can get wrapped up all the way around the updraft at some times, and that creates the rain wrap storm. But yeah, so usually you'll see like a large column of precipitation and then a smaller column of precipitation on the other side. And that's why you get that notched appearance on the radar. And you don't really get this pattern in any other storms. This is like a supercells only type of deal. So yeah, the yellow one are the downdrafts, so the forward flank and the rear flank, and the red is the updraft. So this is like where all the precip is, so yeah, it kind of spreads out. And then the purple lines here, these are the surface winds, so you have this inflow along this boundary here into the updraft, and this is where the outflow boundary is. So this is where that cold air is coming down off the precipitation, and it, as you can see, it's feeding into this updraft. So like this cold dense air will fall out of this rear flanking downdraft, and it will hit the surface, and it will lift up more of this warm, moist air. So this southerly air here is usually warm and moist, and then this air is cold. So that's how it sustains itself. Yeah, so the forward flanking downdraft is northeast of the rotating updraft in the northern hemisphere. So yeah, it's up here. And this is where most of the precip is. This is the original precip. Like, you don't start off with a forward and rear flank. You start off with an updraft and a forward flanking downdraft. And it really has a lot of like hail and heavy rain and stuff. So reflectivity on the radar, which is DBZ, is proportional to precip amount and precip size. So you'll have the highest reflectivity in the forward flanking downdraft. yeah, so here is an example. This is really good. You can also call it like a hook echo. So this is the forward flank right here. So you can see it's like huge, and the updraft is right here. So there's no precipitation where the updraft is. And then your rear flanking downdraft is right here. So it's really small. That's what that hook is. So it's rotating around the storm and into like the edge of the updraft where it's pushing the updraft up more. So the forward flank downdraft forms due to the weight of heavy precip, which drags down the air. And the downdraft is also caused by cooling as the precipitation evaporates or melts as it falls. So this is the heaviest precip in the whole supercell. It's going to have the darkest colors on the radar. Reds, purples, pinks, and even white. But you can also get it can also pull hail around. It can pull rain and it can pull hail. So this is the heaviest precip, and then this is where the tornado would be in the updraft, and then this is the rear flanking downdraft. So the rear flanking downdraft, it wraps a small amount of precipitation around the rotating updraft. The RFD itself wraps around and into the updraft in an inverted comma shape. So you can see it here. It looks like a hook. The precip in the southwest part of the supercell shows us where the rear flank downdraft is and how the winds are rotating around the mesocyclone, and how they advect precip. So it looks like a hook, so it's a hook echo. Hook echo does indicate a mesocyclone is formed, but it doesn't necessarily mean a tornado is formed. You have to look at other stuff on the radar to see if the tornado is formed as well. But if you have this hook feature, that means that you have at least a mesocyclone. Yeah, so I said a tornado's right here. If there is a tornado, it would form right here. I mean, if I look at this, I'm like, yeah, there's probably, like, that's a really good setup for a tornado. But you gotta look at the other stuff, too, to see. This is in Oklahoma. There's Norman. When was this? 1999. Okay. I was 2 years old. Okay. I'm not gonna remember that. So, yeah. The RFD may or may not be filled with visible precip. Precipitation particles are large and very few, and they're difficult to see with the naked eye, so radars can see it because radars are good at seeing large drops. I've seen forward and rear flanking downdrafts in Oklahoma. You can see it sometimes. They don't always have it, but you can see both. Sinking air in the rear flanking downdraft warms and dries as it sinks. So the forward flanking downdraft has a lot of cold precipitation, and the RFD is warmer, but you can get precipitation in the rear flanking downdraft. I have pictures to prove it, but maybe I shouldn't show that because I want y'all to have a life outside of this course. The updraft. So this is the rain-free region of rising air, and it is cyclonically rotating. So the tornado can form between the updraft and the RFD. You need the RFD and the updraft to work in tandem to get the tornado, and I guess we'll talk about that later. Yeah, so this is where I was pointing out, this dry region. So here, again, is the supercell structure. So, it's kind of a hot mess, this diagram, but you can see right here you have this forward flank downdraft. This is where all that heavy rain is, and you have this cold outflow boundary around it. And then you have your inflow into this updraft, and it's like a warmer inflow. And this is where you get the tornado, where you get this mesocyclone. And then you have, it pulls this air around. The mesocyclone pulls this forward flank downdraft around, so you also get this rear flanking downdraft, and it creates this gust front, so this cold air, and it helps to push the mesocyclone up more. And this is kind of the same radar image that we were looking at before. It's just a little different, but it's the same thing. Okay. So we discussed how the rear flanking downdraft and forward flanking downdraft are very different. So this one's the big one. The forward flanking downdraft is very cold. The rear flanking downdraft doesn't have as much precip. It still does have precipitation sometimes, most of the time I would say, but it's warmer than the forward flanking downdraft. And since they're different, they must form completely differently, I guess. So, mesocyclones spin so fast they act like solid bodies, so the air can't really enter the mesocyclone from outside. It's like if you had something and it was like spinning really fast, like you wouldn't want to put your hand in it or like your fingers, like the ceiling fan on your ceiling. Like if you have that on the high setting, like you're not going to put your fingers in there because that would like hurt. That's like more like a solid body. That's kind of the same thing with this. Like it's rotating fast and the air can't really get in. So westerly winds in the free atmosphere that blow towards the storm are stopped by the mesocyclone. And they sink into the ground, and why? Super complicated and not yet completely understood. But they just said that it was acted like a solid body, so it would make sense that if a wind would hit it, that it would sink to the ground. I would say, if they pay me, don't take my idea if this is right and get paid by it. Actually, I don't care. I don't care. You can take this idea and get paid for it. I do not care. Anyway, they spin so fast, they act like solid bodies, so it runs into it, but it can't go through it, so it just has to go down. Like, right? Like, that's what the diagram shows. But how would we know? You'd have to go test it out yourself, and that sounds kind of dangerous, so maybe we'll figure it out with our tourist stuff that we got. Anyway, moving on. So the sinking air gets advected around the mesocyclone due to the cyclonic mesocyclone circulation. Yeah, so it hits it and it wants to move down, but it's rotating, so it spins around. And this is what forms the rear flanking downdraft. Okay, yeah, so it's just the spinning of this air. Like this air comes in and it starts spinning. And so it wraps around the updraft in the supercell, and it pulls the rain around. It really does pull this rain around. So new clouds develop along the RFD outflow boundary as a result of increased convergence. Really? New clouds develop along the RFD outflow boundary as a result of increased convergence and rising motion along this boundary. Yeah, so this is that, this line right here, it's like cold air, and, it creates this boundary, and it increases this upwards motion. So this is the flanking line. Convergence along the RFD may form new supercells, but this is rare. Yeah. Typically no. More likely converts it into a single supercell into a squall line. This is confusing, and I think it can be explained better because it's kind of confusing me. Like, I get what it's saying, but I've always thought of it as, like, this rain precipitation gets pulled around to the other side, which, like, seems more direct and makes more sense to me. But I guess you can also have more clouds form from this rear flank downdraft gust front line, which pushes up the air. But usually, that's like, it's forming this mesocyclone, and I guess it's also forming these clouds as well. And it would appear that it also, if it's moving through this cloud right here, if you have this wind that moves around it, it would move through the precipitation, so it would pull the precipitation around. It would advect this moisture around. So I'm going to go with what I think and say, quite simply, the precipitation is pulled around the storm. I think that is much more succinct. And you can also get some upwards motion from this, but, you know. Anyway. Wall cloud and tornado. So wall cloud, not a tornado, but if you see one, it's kind of cool looking and you might want to go inside. So this is the lowering of the rain-free cloud base under the updraft. So this is where the RFD and the updraft meet. You can get the cloud base to lower and it looks scary, and then if the tornado does form, it will form underneath the wall cloud. And if the wall cloud is rotating, a tornado may form soon. Okay, here's a Twitter link. So yeah, this big thing right here, this chunk, is the wall cloud, and then the tornado formed out of the wall cloud. So you can see the cloud base is super low where the tornado is, so it pulled this base of the cloud low. Wall cloud, lowering of the rain-free cloud base under the updraft, so at the intersection of the RFD and the updraft. So this is the forward flanking downdraft over here. This is the rear flanking downdraft, and you can see there's very minimal precipitation in this rear flanking downdraft. If a supercell forms a tornado, it forms underneath the wall cloud. Yeah, so this is yeah, so this is the wall cloud, and I like to say that the tornado is the rotating updraft. Like, tornado, I guess the updraft is kind of like here, and the rear flanking downdraft is like here, and the tornado is kind of smushed between them. But yeah, anyway, if a supercell forms in a oh, I already said that, okay. Yeah. Oh, this is the same material from the last slide. That always confuses me. They just added a picture. Oh, this is Amanda. She made these slides. She took this picture. Very nice picture. Okay. Is that all? Okay, this is all for today. So we'll get more into it with tomorrow's lecture. Do not forget to take your quiz. It opens Monday, which is the day this lecture is scheduled for. It opens at midnight, and it will close Wednesday at 11:59 this Wednesday. So good luck. Watch the lectures from last week, lectures 6 through 10. And next week's quiz, which will also open next Monday and close next Wednesday, will be on lectures 11 through 14. So this lecture is for next quiz, not this one coming up. So good luck. Email me if you have any questions. Bye!